This conference will now be recorded.
Okay, so where we left off on Wednesday, we'd gotten right up through kind of the earliest or the simplest uh, aspects of ventilation, really just talking about pressures, right? Transpulmonary pressure, intrapulmonary pressure, intrapleural pressure, so on and so forth, and the kind of the general relationship between those things and atmospheric pressure. What we're going to do now is kind of take a look at how we physically manipulate those pressures to result in inspiration and expiration, right? How are we going to physically lower intrapulmonary pressure? How are we going to raise intrapulmonary pressure, right? How do we do those things relative to atmospheric pressure? And the way that we're going to do that is deceptively simple. We're just going to change the volume of the thoracic cavity. The larger the cavity, the lesser the pressure. The smaller the cavity, the greater the pressure. And in doing so, we'll raise and lower that pressure relative to atmospheric pressure. Air will come in or air will go out one way or the other until they reach equilibrium. Inspiration or breathing in, right? This is, we're going to call it an active process in that it requires muscle action to make it happen. Okay, we can't just sit back and let it happen. We have to physically do something. And so the inspiratory muscles, these are the diaphragm and the external intercostal muscles. So we have muscles between your ribs. We'll look at a picture of this in a little bit. The ones on the outside are going to be involved in lifting and separating the rib cage, making the internal cavity there larger. The diaphragm, when it contracts, pushes down, as we've discussed a handful of times throughout the course, right? And by pushing down, we lower the floor of the thoracic cavity, again, making it larger. By increasing that volume, we decrease the internal pressure, right? That intrapulmonary pressure below atmospheric pressure. Okay, and this is going to cause air to flow into the lungs under that pressure gradient, right? Outside greater than inside, so air comes in. Okay. Now there's this sort of the normal sitting down, taking a normal breath kind of inspiration, and there's also what we call forced inspiration, which is when we go kind of beyond that resting breath, okay, and we go into a deep breath, maybe is the best way to put it, okay. And so you can do this consciously, right? This can happen as the result of vigorous exercise or COPD, chronic obstructive pulmonary disorder, anything that's going to result in your oxygen intake being insufficient. Okay, we're going to see larger than normal breaths, gasping type breaths. And to do that, we're going to bring in, okay, in addition to the external intercostals, in addition to the diaphragm, we're going to bring in things like pec minor, sternocleidomastoid, the scalenes. Again, all there to kind of pull up and out, right, and expand that rib cage as much as we possibly can. And by doing so, we expand the inner lung surface and bring air in at a greater clip than we see under a normal breath. So in terms of the musculature here, what are we really looking at? Obviously, at this point, we don't have pec minor or sternocleidomastoid or scalenes on here. It's just these external intercostals here, right? You can see them connecting adjacent ribs and the diaphragm below. And the idea here again, to lift and separate, we pull those ribs up and out. The opposite of breathing in, right? The opposite of inspiration here is expiration. And this can be a passive process. Okay, so as you sit and listen to this lecture, your breathing is probably not labored. You're probably not really huffing and puffing. Okay, you're certainly probably not speaking. Okay, so this is very much just going to be kind of a letting go. All right, we forcibly expand the rib cage and then we just kind of relax. And we can let the elasticity of the stroma, right, all of those elastic fibers in the lungs, we can let that bring the rib cage, bring the thoracic cavity back down to its normal resting volume, right? And as we get smaller, right, pressure goes up. Eventually pressure exceeds atmospheric pressure. And now our pressure gradient goes the opposite direction, right? And so air flows out of your lungs and out of your body, right, simply because of that pressure gradient. Now, just like you can have a deeper than normal inspiration, you can have a deeper than normal expiration as well. So there is forced expiration. Forced expiration requires muscle activity. Okay, so it is an active process. So this is going to require predominantly the obliques, okay, but also the internal intercostal muscles as well. And what those are going to do, so the oblique muscles here are going to compress the abdominal cavity and force the stuff in there up, right, and into your thoracic cavity, doing the opposite effect of what the diaphragm does. The internal intercostals are going to pull the rib cage down and in. Okay, pull those ribs closer together, and again, effectively minimize the internal space there. Is really all this is trying to demonstrate, right? Just this idea, and then the internal intercostals here aren't illustrated, but they are there. As far as what this means for pressure through this phase, there are really, again, two different pressures we have to worry about relative to atmospheric. Okay, so as we, if I can find my cursor again, as we breathe in, right? So the course of the average breath is about 5 seconds long. Okay, so you need to take about several of those per minute. As we breathe in, right? We inhale, air comes in, then we begin the expiration process and air goes out, right? That's the usual thing. While this is happening, in order to make these things happen, we're seeing internal pressure changes. Again, these numbers are relative to atmospheric pressure, so 0 is at atmospheric pressure, positive is above atmospheric, negative is below it. Here is our intrapulmonary pressure, right? So the pressure inside the lung. As we breathe in, okay, as we inspire, we see a dip in internal pressure, but it comes back up to 0 as air continues to flood in, and eventually those pressures equalize. Right? And by the same token, when we breathe out, right, initially we have a rise or a spike in pressure, right, but that declines as air leaves the lung and those pressures equalize again. While this is happening, right, that intrapleural pressure, the pressure that is holding the lung open, okay, against that elastic stroma, this is always going to be less than that intrapulmonary pressure, okay? And so it will decline as intrapulmonary pressure declines and raise as intrapulmonary pressure rises, right? But always maintaining roughly a pressure gradient of about -4 millimeters mercury, give or take. Higher or lower at different points, but that's roughly where it's going to be. Never higher. Actually, it's always going to be 4 or less. 5, 6, something like that. Now, in terms of what might affect the rate of air entering or leaving your lung, there are really 3 big things that are going to be resistant or hindrant to it. Okay, this is just regular old airway resistance, surface tension in the alveoli, and lung compliance or lung elasticity is another way to put that. Now, I'm not going to be overly worried here about you remembering all of these things, all of these different parts of airway resistance here, largely because it's usually not a big deal. Airway resistance is usually a pretty small factor here. And the reason for this is quite simple. The initial pipes coming into your airway are pretty large, right? And it's not until we really get down into some of the little nooks and crannies, right, that we're going to start seeing smaller airways or smaller passageways. And it's really only at that point that we see much in the way of resistance. Okay, and beyond that, once we get down to the terminal bronchiole, there's no resistance there at all, right? It's essentially gone, and all that happens there is diffusion. So if we look at our little pathway here, right, conducting zone into respiratory zone, resistance is pretty negligible at the beginning. So even though we're all the way up here on our graph, right, you notice there's no numbers on it, that's still pretty negligible. It's essentially non-existent. And it does increase, right, as the pipes themselves get smaller. But as soon as we hit those medium-sized ones, we see a really sort of rapid decline. And by the time we get down to the respiratory zone, there's no movement of air at all, and everything is diffusive at that point. So pressure, or rather resistance, is zero. Now, there are, of course, going to be issues where airway resistance becomes a sort of a bigger factor. Okay, so you'll see labored breathing or sort of strenuous breathing on the side of that. And this is usually going to be, again, an obstructive pulmonary disorder. So anything that's going to prevent air from moving freely through some of those medium to large pipes is going to be really the biggest issue for us. The sort of immediate treatment of something like this is going to be epinephrine to dilate those bronchioles, to dilate those smooth muscles, and try to get them as open as possible. So something like an asthma attack or something like that is usually treatable with epinephrine. A surprisingly important factor here, and something that we've already touched on a little bit, is surface tension or water tension, right? Again, it's not something that you and I really think a whole lot about on our daily basis. I mean, I assume. Certainly I don't. Because at the scale that we live our lives, water tension is a negligible force. It's so small as to be non-existent, okay? And we really only notice it when we overfill a glass or whatever, and we get that meniscus on the top. But at the scale of the alveolus, it's really, really powerful, okay? And can be sufficient enough to collapse alveoli. Right? And we can actually get them down to the point where they are closed off. And so the way that we're going to resist this, right, is with those type 2 cells, right, the ones that are out there secreting surfactant, okay? And again, that's just a sort of a fatty, proteiny kind of a thing, kind of in the same fashion as, like, say, myelin would be. But it's there to break up that surface tension. It's there to kind of hold water molecules apart so that their attractant forces are fairly weak and prevent this from causing alveolar collapse. Now, you don't start producing this stuff until just before you're ready to hatch, right? Because when you're in utero, there's no reason to. You don't have any air in there anyway, right? There's nothing filling your lungs. So one of the issues with preemies is, and kind of always has been, a lack of surfactant produced. Okay, we call this infant respiratory distress syndrome. Basically, the problem there is that they're trying to breathe, but they don't produce any surfactant, and so their alveoli are continuously collapsing. So that's why so many preemies end up on ventilators and things like that, because they are still developing. The development that would normally happen in utero is happening ex utero, and so they need a little bit of help. Eventually, they'll get to a point where they would normally have been born. They'll make their own surfactant at that point. They can be taken off the vent, but that's something that we see fairly common with preemies. And the last factor here, compliance, right, or stretchiness, elasticity, right, willingness to expand, okay. Sort of in the same way that we can talk about like a heart valve being sort of wimpy or normal or stenotic. We can talk about lung tissue kind of being normal or stenotic. Typically, lungs are fairly easy to expand. You may have seen sort of people blowing up like sheep lungs with a straw or something like that in various science courses and things like that. They're very, very easy to expand by design, right? They are not meant to really resist expansion. But, okay, like all of the things, when we start seeing tissue damage, so particularly fibrotic damage, where we have some of that stroma, that connective tissue that is not particularly mitotic, right? That gets replaced with collagen fibers, right? It fibroses. And collagen fibers don't stretch, right? That's their whole point. So we lose some expansibility, we lose some stretchiness there. If we have a disorder or some other means of sort of lowering the production rate of surfactant, again, we can lose compliance there. Or as you get old, okay, the costal cartilages tend to calcify, right? They don't ossify, but they calcify. And as they calcify, they become less flexible. As they become less flexible, the rib cage itself is capable of less expansion. Okay, and so old people have lowered lung compliance typically because of no other reason than simply that calcified cartilage there. Other things that can go into this, if you have a spinal, right, and you have partial paralysis, right, this can lead to that, particularly of the intercostals. If you have deformities of the thorax, so something where we might see, like, say, scoliosis or some other spinal abnormalities, some abnormal curvatures there, can do this as well. As we try to utilize this stuff as a diagnostic tool or as a measurement tool for relative health, the easiest place for us to start is by simply measuring how much air can you move, right? What we'll call respiratory volumes. And these respiratory volumes, the tidal volume, the IRV, the ERV, the RV, are all related to normal breath, forced expiration, and forced inhalation. And then, of course, there's always going to be air that never leaves your lungs, that's stale air. So, what does all this mean? So we're going to just start with the top part of this, the colored part of this for right now. Okay, your tidal volume is about half a liter. Okay, male and female both. Not big differences there. And this is just the amount of air as you're sitting down right now, the amount of air that you breathe in or out with each breath. So you inhale about half a liter, you breathe that half a liter back out again. That's your tidal volume, your normal resting breath volume. The amount of air you can breathe in above that, so if you take a really big deep breath, okay, everything above that is the IRV, or the inspiratory reserve volume. And here we do see a very, very large sex difference. Men have an average inhalation, or IRV here, of about 3 liters compared to about 2 for women. Okay, and again, this is varies person to person, but men typically have a larger rib cage and so have a greater expansibility of it. That's really all that is. The ERV is kind of the same thing, but in the opposite direction. This is, you take your normal breath out and then you keep going, right? And how much more air can you breathe out? And this is significantly less. This is about a liter, right, for both men and women. Men are a little bit higher at about 1,200 mils. Women are a little bit lower, about 700 mils. But again, kind of in the range of error there. And then the residual volume is, again, about a liter, a little bit north of a liter. And this is the air that never leaves your lungs. There is always going to be stale air in there because, again, your lungs don't collapse, right? And so all of the air, more or less, in the respiratory zone stays there forever, okay? We can take those, right, those various volumes, and we can combine them to put together maybe more functional terms here we'll call capacities, right? So this is the inspiratory capacity, the functional residual capacity, the vital capacity, and total lung capacity. Okay. And the easiest way for us to look at that is to use spirometry here. And spirometry is just the method by which we measure volumes of air in and out of your lungs. Here is our spirograph of a adult male. Here's a tidal breath, so in and out, right? And so the up and down here, right, this measurement, that's our tidal volume, okay? And then we ask him to take a big deep breath. So we have all of this air moving in. And so the tidal volume and the inspiratory reserve volume above that in the darker color. You get the idea, right? Our capacities then are going to be combinations of 2 or more of these volumes. So the inspiratory capacity is the total amount of air you can breathe in at a deepest possible breath. So this is tidal volume plus the IRV. The functional residual capacity is the air that never leaves your lung during a normal breath. Right? So at a tidal volume type breath, a certain amount of air never goes anywhere. Okay? So that's the ERV plus the residual volume. Vital capacity is deep breath in, deep breath out. How much total air can you move? Okay, so that's the IRV, the tidal volume, and the ERV put together. And then if we put all four of them together, right, we get the total potential volume of your lung, the total lung capacity. Now, this residual volume exists for a couple of different reasons. One reason, of course, is that there is no airflow in the respiratory zone. Okay, that air is perfectly still; it doesn't move. Okay. The other reason that there is residual volume is dead space. Okay, so we've got anatomical dead space. This is basically the volume of your conducting zone. Right. And this is about 150 mils on average for a person. So a relatively small component, about a tenth or maybe a little bit more of the total residual volume. And then the remaining here is what we call alveolar dead space, or places where we've got obstructed alveoli or collapsed alveoli beyond that. And so the total dead space then is a sum of those two things. But again, most of the dead space is just what happens to be in your respiratory zone, that air that doesn't move. We're going to use these capacities and volumes as part of various function tests or functional tests. And again, the instrument we use here is a spirometer. It's a relatively simple thing. It can be as simple as a tube connected to a little sort of graduated cylinder with a like a plastic bead in it, or it can be a big fancy machine. Okay, in either event, it's just as hard as a tube you breathe into, right? And we have some mechanism for measuring the passage of air, the volume of air that moves through there. And part of the reason that we do this is if somebody comes in and they say, hey, I'm having trouble breathing, spirometry can tell us, give us kind of a first pass here. Are we dealing with a OPD, right, an obstruction, or are we dealing with a restriction, right? Is there a blockage, or are we losing our compliance? Okay, and so the difference there is be which things go what direction, right? So if we see increases in things, right, TLC, functional reserve capacity, residual volume, these are typically going to be obstructive in nature. If we see those same things decline, right, or vital capacity decline from where it should be, okay, these are typically going to be restrictive disorders. Okay, so again, giving us kind of a first pass as to where to begin looking for not only root causes, but of course also treatments. For really more sports medicine type applications, training, things like that, but also things like geriatrics as well. This is where we kind of focus on, say, rate of movement, right? Particularly for athletes, but again, for elderly people here as well. And so we measure things like forced vital capacity or forced expiratory volume. Here, we basically just say, how much can you breathe out, right, if you take a deep breath? And then from there, how much can you do that over the course of a certain set of time? Okay, so you take a deep breath, breathe it out, and then you breathe it out as much as you possibly can, right? And then you do that for a minute, right, or 30 seconds, okay, or whatever, and we get a forced expiratory volume as kind of our ultimate measure of that. Another way to get around this is to look at alveolar ventilation. By this, we're going to measure what's called minute ventilation. And this is the total amount of air that moves in or out of you in 1 minute. Okay, so basically the simplest way to do this, right, is to take your tidal volume and the number of breaths you take in a minute, right? And from there, we end up with your minute ventilation, right? So again, on average, right, you take about 20 breaths a minute. And you do this at about half a liter per minute, okay, which gives us 6 liters per minute, right? We can move that up to maybe 200 liters per minute, okay, dependent on our fitness, okay? And it's a simple test, right? It's a very simple, easy thing to measure, but like most simple, easy things, it's maybe not the best measurement of efficiency we could possibly get. If, on the other hand, we want to get maybe a better indicator of actual ventilation, we'll get to what's called AVR, okay, or alveolar ventilation rate. And this is the flow of gases in or out of an alveolus during a particular moment in time. The way we're going to get this is frequency multiplied by total volume minus dead space. Okay, so again, it's just taking some of the things we've already measured, right, and kind of tweaking them a little bit. And that's, like I said, it's a little bit more complicated, but it is, I think, a more effective indicator of pulmonary health. Okay, so we've moved air in, we've moved air out, and that's all well and good, right? But the whole point of doing all that is to exchange gases, right? To mix atmospheric gas with blood gas, and then later on, after circulation, to mix blood gas with extracellular fluid gas, which is external respiration and internal respiration. They're both going to operate under the same basic set of principles, so there's not going to be anything new or wacky about internal versus external. They both kind of do the same kinds of things. They're more or less reliant on the same set of properties. There are going to be a handful of rules and laws that we have to kind of have a basic understanding of in order to understand what's happening here. And the first of these is Dalton's law of partial pressures. And basically, Dalton's law of partial pressures is basically this. Whatever the pressure of a gas is, okay, we can figure out the contribution of each gas by the total proportion of that gas in the total thing. What that means is, it sounds complicated, what that means is if atmospheric air is at 1 atmosphere, okay, and atmospheric air is 21% oxygen, which it is, right, the partial pressure of oxygen is 0.21 atmospheres, right? Simple as that, okay? So what we look at here are partial pressures. And the same basic thing that's going to affect all other diffusions affects us here. We flow from areas of high pressure to low pressure, right? So if the partial pressure of oxygen in atmospheric air is 0.21, and that's higher than the partial pressure of oxygen in the blood, then oxygen moves into the blood, and vice versa. Another maybe not obvious gas law that we have to worry about here is Henry's law. And Henry's law here basically tells us that the greater the pressure gradient, the more gas diffuses into a liquid. That's it. Okay. Now, there are additional little aspects to this, something called solubility, right? So not every gas wants to go into a liquid at the same rate. Oxygen does not like to dissolve in water. Carbon dioxide loves to dissolve in water. So carbon dioxide has a higher solubility, right? And so all other things being equal, okay, more carbon dioxide will dissolve into water than oxygen will. For our purposes, what this means is, if we want to transport a lot of oxygen in the blood, we have to do it some other way than simply dissolving it in the blood. This is why we have hemoglobin, right? Because oxygen has such a low solubility, we have to have another means of transport. We don't have a special thing for carbon dioxide because carbon dioxide will gladly go into water, right? And it will gladly dissolve in your plasma. Okay? That's really the key part of this whole thing. Okay. So as far as the air in your lungs, right? Remember, the air in the respiratory zone doesn't move. It's stale. It is always stale. It will always be stale. Because of that, alveolar gas, the air inside your alveoli, is more carbon dioxide and water rich than atmospheric air. It's just going to be one of those things, right? But, okay, it's still going to be oxygen enriched enough, okay, for our purposes. It's not going to be quite as nice as atmospheric air. It's always going to be a little bit less, okay, but it's still going to be enough. So our first respiratory process then is going to be exchange between that alveolar gas and the blood. Okay, bringing in oxygen, dropping off carbon dioxide and water vapor. Okay. Now there's a lot of things going on here. Really, the key part of this whole thing for us is the fact that if I can get my cursor back here, the membrane itself is going to be relatively thin. Okay. And then, of course, the changing partial pressures of both blood and alveolar gas. Ventilation perfusion coupling we'll talk about, but it's a slightly different issue. Okay, so the respiratory membranes, like I said, very, very thin. Half a micron to maybe a micron thick, right? But that thinness enables us to have a massive amount of surface area, okay? Roughly 40 times the surface area of your skin inside your lungs, which is pretty wild. One of the dangers of pneumonia, and part of the reason that pneumonia will kill you, is not physically fluid filling the air spaces themselves, but fluid expanding the respiratory membrane, expanding the walls of the alveoli. Okay, and when they get thick, you don't drown because you have fluid in there. You drown because your membranes are too thick to adequately exchange gas. Okay, you can't physically bring enough oxygen into your blood if the membrane is too thick. Okay. Our partial pressures here, okay, are going to be the main drivers of gases into or out of the blood. There is a pretty massive pressure gradient for oxygen. Okay, blood coming into your lungs is at a partial pressure of oxygen of about 40 millimeters mercury. Even though it's less than the atmospheric air, alveolar partial pressures of oxygen are about 104 millimeters mercury. Okay, so that's a big gradient, right? And that's really going to force oxygen into the blood fairly rapidly. Okay, so we basically bring our blood partial pressure up to meet the alveolar partial pressure in about a quarter of a second. Just pretty good. Okay, a red blood cell inside a pulmonary cavity is usually there for about 3/4 of a second. So we have lots and lots and lots of time to get this stuff saturated. What this means is you can increase perfusion rate through your lungs by 3 times and still be fully saturated. Okay, it gives us a big safety factor in there. So if we look at kind of the experience of a red blood cell, right, moving its way through a pulmonary capillary, again, it takes about 3/4 of a second, and usually we are fully up, right, by the time we've been in there for about 1/4 of a second. Partial pressure gradient for carbon dioxide is not quite so, okay, about 40 millimeters. Venous blood, partial pressure about 45. Okay. Now, that said, right, it doesn't have to be as steep, right, because so much more carbon dioxide is soluble in plasma or water, right? It'll still diffuse at roughly the same rate that oxygen diffuses in, even though the gradient is significantly lower. So if we look at a little chart here, right, and I don't want to go through the whole chart, but basically the idea is we get big changes in partial pressure of oxygen, right? lot in arterial blood, goes way down at the tissue, right? And in the venous blood, and then back up again. But our partial pressure of carbon dioxide doesn't really change. Arterial blood, alveolar gas, tissue, extracellular fluid, venous blood, it's pretty much always in that 40 millimeter mercury, 45 millimeter mercury range. Okay? And a part of this has to do with how we transport carbon dioxide in the blood, right? It's going to be a part of, as we'll see, maybe today, maybe Monday, part of the carbonic acid bicarbonate buffer system. So we need a certain amount of this stuff in your blood to maintain a pH. So we don't necessarily want to drop all of it off, right? We still want to maintain a reasonable partial pressure, even in arterial blood. Then when we get to internal respiration, so we have arterial blood being delivered to tissues, okay? Here, our PO2 in the tissues is always lower than arterial blood is, which means that we drop oxygen off, right? Our partial pressure is highest in the blood, so we go from high pressure to low pressure. That's all that is, okay? So that's what causes hemoglobin to disassociate from oxygen, that partial pressure gradient pushing it out, okay? And by that same token, okay, we have carbon dioxide being forced in, all right? Again, simply because of the pressure gradient. And again, same basic process happening there. Now, because oxygen and carbon dioxide differ so strongly in terms of their solubility, we, as we mentioned, have different mechanisms for transporting them, right? Oxygen transport, there is a little bit that gets dissolved in the plasma, right? About 1, maybe 2, maybe 1.5% of the total oxygen is dissolved in plasma. But the vast majority of it, 99% of it, has to be bound to hemoglobin, right? Again, simply because it's just not soluble, right? One of the profound challenges for things like fish, right, living in water, is that water holds so little oxygen compared to air, right? It just really isn't an ideal mechanism for transporting it. One thing that's interesting about the, we'll call the saturation curve for oxygen, is that it's not linear, right? The willingness for hemoglobin to let go of its oxygen is not constant. And for most of the partial pressures that we're going to experience, okay, hemoglobin is really unlikely to let it go. It's not until we get really, really low, right, say go from 100 millimeters mercury to 40, like we see in the tissues, that we even get rid of 1, right? This curve, this saturation curve, there we go, where that cursor go, right? Come on, is extraordinarily flat at the top. I don't know why I'm having some trouble with this cursor here, but I am. Okay. And it's not until it doesn't get steep until we get really, really low. What this means for us then is that we're going to hang on to 3 out of those 4 oxygens, right, all the way around back to the lungs again. Okay, it gives us what's called a venous reserve. It enables us to deliver oxygen where it has to go, but hold on to most of it and in, come on, cursor. What the fuck's going on here? It's going to be down in this zone right here, right, where it's really, really, really low, okay, and we'll drop off more oxygen at that point. But we're otherwise going to be unwilling to part with more than 1 of those 4. So again, right, we're talking about equilibrating with arterial or alveolar gas in the lung, right, where pressure is at about 104 millimeters mercury. Your blood is going to top out at about 100 millimeters mercury, right? That's about 20 mils per 100 mils of blood. So 20% by volume is oxygen, which is a lot, right? And on average, your hemoglobin is going to be about 98% saturated. So not maybe 100%, but close enough, right? 2 out of every 100 will have 3 instead of 4. Any oxygen enrichment. So if you are to, say, be put on oxygen, if you're otherwise pulmonary health, your pulmonary health is good, being put on supplemental oxygen won't actually do a lot for you, okay? Because at 104 millimeters mercury in the alveolar gas, we're 100% saturated, right? There's a little 2% room for error there. So if you start pumping in pure oxygen to a person, you can only increase that saturation 2%, right? Then you're going to be at 100%. So there's not much that, for a healthy person, that supplemental oxygen is going to do. Venous blood, okay, again, we drop off oxygen, okay, usually one of those 4, right, but we do drop them off. And this is going to drop our partial pressure down to about 40 millimeters mercury. We lose about 5% per volume oxygen, right? And hemoglobin here is 75% saturated, right? 3 out of 4 instead of 4 out of 4. And again, this concept here, this gives us this venous reserve, right? This idea that if we need it, right, you can increase oxygen delivery without having to, without having to increase either cardiac output or ventilation rate, right? You have extra that you can give if you need it. And that's a pretty powerful thing. One of the big advantages to this, advantages to this non-linear exponential association or dissociation curve, depending on how I look at it, with hemoglobin and oxygen, is that because the upper end of this curve is basically flat, you can be in a place, you can be at sea level, where partial pressure is 0.21 atmospheres. You can move to Denver, where partial pressure is more like 0.18 atmospheres, okay? And you can still essentially fully saturate your blood, right? Your hemoglobin is going to want to bind and attract and pull oxygen so firmly at such a wide range of partial pressure, right? You can be at 8 alveolar partial pressure and still be functionally fully saturated, right? Very, very powerful for us in terms of picking oxygen up, okay? The other half of this that becomes powerful for us, right, is the other end of this curve. Where'd my cursor go? Not that it wants to listen to me today anyway. I don't know what that's all about. Yeah, never mind. The other end of the curve, the lower end of the partial pressure thing here, right? Where once we start letting go of oxygen, we very quickly let go of all of it, right? So if a tissue is in dire need, it will get the oxygen that it needs. Now this curve will shift right depending on a variety of different factors, okay? So temperature, concentration of free hydrogen ions, pH, you know what that is, partial pressure of CO2, right? And a chemical we produce called BPG. And each of these factors operates basically the same way, right? By modifying the attractiveness of oxygen for hemoglobin, changing the rate at which it will bind to it, okay? So increasing temperature, so making your body warmer, increasing carbon dioxide partial pressures, releasing BPG, decreasing pH, okay? All of these things make oxygen and hemoglobin less friendly. Decreasing any of those things makes them more friendly, okay? So if we look at some curves here as to why this is, okay, what's happening here, right? Simply of just, in this case, body temperature and PCO2 or pH. If our normal body temperature is about 38 degrees C, decreasing that, right, shifts our curve to the left, which makes us less likely to give up oxygen at any partial pressure. Increases in temperature, move it to the right, making us more likely to drop it off. And the same thing here for carbon dioxide or pH. The more carbon dioxide we shift to the right, make it less or more likely to drop off. With less carbon dioxide, we shift to the left, less likely to drop off. And the reason for this is quite simple, right? If we think about where your body is using oxygen, right? It's using oxygen for various chemical purposes. It's an area of the body that's burning through a lot of ATP, right? In doing so, right, it's using up a lot of oxygen and producing a lot of carbon dioxide. So the places that need oxygen are going to be warmer with more carbon dioxide and a lower pH, right? And so those three conditions, right, are going to shift our curve in such a way that we're more likely to give them oxygen. And areas that aren't working hard, that don't need the oxygen, are going to be cooler, and there's going to be less CO2. So we move the curve left, and we make it less likely to give oxygen to those tissues, right? It's as simple as delivering it where it needs to go, right? I think that's probably a good place for us to stop. I don't want to get into transport of CO2 because we won't finish it, and we'll get halfway through it and no one will remember it. So we'll call it there. I will see you guys on Monday. We will finish off respiration. The study guide did get posted, so make sure you take a look at that. And if you guys have any questions, let me know. Have a good weekend. Be kind to one another.